for the second part of this lecture, I'm going to discuss more macroscopic aspects, and I will focus on thermodynamics. But you will see that the contact parameter, which is related to microscopic two-body physics, will again appear now and then. So thermodynamics is essentially the theory or the science of heat. And as I told you, measuring temperature for strongly correlated system is very difficult. And to begin this second part, I would like to show you a way to measure temperature or to measure the thermodynamical property, which is very smart, and I like very much. That was proposed, that was illustrated for the first time, I think, by the group of John Thomas and also a bit by the group of J.B. Jean. And their idea was not to focus on the temperature, but rather to go back to your very first lecture of statistical physics, where you were looking at the microscopic and the microcanonical ensemble, which is characterized by some equation of state that relates the energy E of the system to the entropy. So the energy of a cold atom gas is actually quite simple to measure. So when you look at the energy of your cloud, it's made of three terms. So the kinetic energy T, the interaction energy I, and the trapping energy V. So we've said already that T was infinitely large, I was infinitely large but negative, and these two were giving you some finite result. And V is always finite. And these two quantities, T plus I and V, are actually very easy to measure. So T plus I is also called the released energy. It's the energy that you measure when you make a time-of-flight experiment. Because what happens when you make a time-of-flight experiment? So I come back to my first slide. You have your strongly correlated system. You turn off the trap. The cloud expands. So it means that its density decreases very fast. And so it means the interaction energy decreases very fast. By conservation of energy, it must go somewhere. And the somewhere is in the kinetic energy, because you don't have any potential, trapping potential anymore. So you convert in T plus I, you convert I into T. So very fast, after a few characteristics time correspond to the trapping period of your potential, all the interaction energy is converted into kinetic energy. And so now you have some free flight expansion. And so you have, after a long enough time of flight, a picture of the momentum distribution after the interaction energy was converted into kinetic energy. And so by taking a picture and calculating the second moment of this distribution, you have access to this kinetic energy, which is equal to T plus I. So measuring a time of flight is actually, a time of flight experiment is actually a measurement of T plus I. Measuring V is even easier. You just have to take an in situ image of your cloud, integrate this density profile by weighing the density by the trapping potential, and you just have V. So V is just obtained by taking a picture in the trap. So E is actually quite simple to obtain. S, the entropy, might not seem so simple. But again, if you're smart, and the guy who did that were really smart, using the fact that you have Feshbach resonances that allow you to control the strength of interaction, it's actually very simple to measure the entropy of this kind of system. So let's take a system which has some finite and possibly infinite value of the scattering length, and you want to know the entropy of your system. So what you just do is to make an adiabatic ramp of magnetic field to bring you to a point where the scattering length is equal to 0. So in this case, you have simply an ideal gas. And I told you that everything is simple for an ideal gas. You can measure temperature, you can measure density, you can measure everything, because you know perfectly well the behavior and the thermodynamical properties of ideal gases. So you can make, for instance, a time-of-flight experiment, measure the temperature. So you have T over Tf. And since you know all the thermodynamical properties of an ideal gas, knowing T over Tf, you know the entropy, S. So you know the entropy of your ideal gas. But now, the ideal gas is related to the initial system just by an adiabatic ramp. And if your adiabatic ramp was indeed adiabatic, the entropy must have been conserved between this point and that point. So it means that S here is exactly the same as S there. And so, you know the entropy of your initial system. So actually, it's very easy to measure the microcanonical equation of state of your system. And so that's what was done by the group of John Thomas in 2007. So they measured, so these are the dots here, the entropy as the function of the energy. For instance, you can also then extract the temperature by using the fact that D equals TdS, so you can have access to the temperature of your system. And they could compare it to several theoretical calculations, so Monte Carlo, diagrammatic methods, so they are here. But you see that they were not constrained by a specific model. They could plot their equation of state without any reference to any kind of model, and then compare afterwards to all the theories that were proposed by theoreticians. Okay, just a little side remark, which will be a nice illustration of scale invariance in cold atoms, and will provide again some illustration of these exact results that you can obtain using very general arguments. Actually, when you calculate or you measure the release energy or the trapping energy of your system, you don't have to do the two measurements, especially at unitarity, when A is equal to infinite. Because you have, for this strongly correlated system, some very old theorem that relates to the release energy, the trapping potential, and here's the derivative of E with respect to 1 over A, which is nothing but the contact. So you have a relation between these three quantities, released energy, potential, and contact. And for instance, when you are at the unitary limit, 1 over A is equal to 0, so this is just equal to 0. So you have that the released energy is just equal to the potential energy, trapping energy. So actually, when you want to measure the equation of state here, you don't have to measure both the released energy and the trapping potential energy. You just have to measure one, and you have the second one immediately using the Vero theorem. So I would like to demonstrate this relation. And it's based on very simple dimensionless analysis, and so Rudy will like it because there are lots of length scales in the problem. So I'm working with an ensemble of fermions again, could be bosons, let's say fermions. They are in a harmonic potential, so it's harmonic in all three directions of space. And so I want to know the energy of the system. So this energy will depend on, a priori, all the physical parameters of the system. So there is h bar, the Planck's constant, the mass of the particles, the scattering length, the trapping frequencies. So there are 3 trapping frequencies, and the number of atoms. These are the only physical quantities that I have if I work at 0 temperature. I'm dealing with the ground state here. It works also at finite temperature. So now I'm going to make some dimensional analysis and look at what is the general scaling of this equation. So I must first construct something which is an energy. So let's say the natural energy scale is h bar square divided by ma square. So it's the binding energy of the dimer associated with the scattering length A. And then I must have some function of all the dimensionless numbers I can construct from these quantities here. Essentially, these dimensionless numbers can be written as ratios of length. So I have one length here, A, and so I can build other length scales by taking h bar m and omega alpha and constructing the size of the harmonic oscillators along the direction alpha. So it's going to be a function of L alpha divided by A and M, of course, where L alpha is equal to square root of h bar divided by M omega alpha, and I'm going to call U alpha this ratio L alpha divided by A. Okay, so this is the most general form, which is compatible with dimensional analysis. So now let's look at the contact. So the derivative of E with respect to 1 over A. So there will be two terms. So I can first derive this term here. So it's 2 h bar squared divided by MA times F of L alpha times A n plus, well, I have A which is here. So the sum over all directions alpha of h bar squared divided by MA squared times L alpha times the derivative of F with respect to U alpha. So this is almost the energy up to a factor A. So this is 2A times E plus h bar squared divided by MA squared times the sum over alpha of L alpha dF divided by du alpha. So this I know, this I know, this I don't know. So I would like to express dF divided by u alpha. So u alpha, I remind you, is a function of L alpha divided by A. So when I differentiate with respect to u alpha, I can either vary A, which is what I've done here, or vary L alpha. So h bar and m are difficult to vary, so I can vary the frequency of the trap. So I'm going to look at the derivative of E with respect to first omega square alpha. So it's using the Hellman-Feynman theorem, it's also the expectation value of the derivative of H with respect to omega square alpha. But if I look at the Hamiltonian, so I haven't written it explicitly, but there is a kinetic energy term which do not depend on omega alpha. There is an interaction term between particles which do not depend on omega alpha, and omega alpha enters only the trapping potential. And it enters by m omega square alpha divided by 2x square alpha. So this is actually the mean value of m over 2 times x alpha square. So if I calculate the sum over alpha of omega alpha square dE of d omega alpha square, this is just V, the trapping potential. So this is according to Hellman-Feynman theorem. But now I want to re-express this expression here as a function of my unknown function f here. So I write that sum over alpha of omega alpha square dE of d omega alpha square is also equal to 1 over 1/2 sum over alpha of omega alpha dE divided by d omega alpha. So I use this expression for E. So this is going to be 1/2 sum over alpha of omega alpha d of L alpha divided by omega alpha 1 over A dF divided by du alpha. And dL alpha divided by d omega alpha is just minus 1/2 L alpha divided by omega alpha. So this is going to be minus 1/4 of sum over alpha L alpha divided by A dF du alpha. So if I compare these two expressions, I see that the sum over alpha of L alpha dF divided by du alpha is equal to minus 4A times V. And so there's a factor h bar square over MA square missing here. So now if I combine this and that, what I obtain that dE divided by d1 over A is 2 times A times E minus 4 A times E. And so if I write that E is equal to T plus I plus V, what I get in the end is that this is 2 times T plus I minus T. And so I get the expression that's given here. And so actually this Vera theorem was proposed for the first time again in that paper by the group of Debye, where they could compare T plus I minus V to the contact that they obtained using the 3 different methods I've shown you. And here again you see that the comparison is very good between these 2 quantities. So this is again a test of the relationship between the contact, so the information about short-range correlations, and the macroscopic quantities, so released energy and potential energy, via this Vera theorem. Okay, so now we'll finish my lecture on trying to relate what's happening in a trap with what theoreticians usually prefer. That is to say, something that happens in a box, in a homogeneous potential, in a homogeneous system. Because what I've discussed here, so the Vera theorem or the microcanonical equation of states, is a global measurement. You measure the global energy of your system, the global entropy of the system, and all these global quantities. So you don't know what's happening locally in the system. So you're dealing with something which is explicitly trapped in a harmonic potential. And this actually relies explicitly on the fact that you are in a harmonic potential. And of course, when you ask theoreticians to work in a harmonic potential, they don't really like, because things are sometimes more complicated in a harmonic potential. Although there are some simplifications to the fact that you have well-defined bound states. And so I would like to show you a very simple way to relate what's happening in a trap with what's happening actually in a box. And again, using only very simple assumptions. And so the main point here is going to be the local density approximation. So the local density approximation relies on an assumption that people who are doing mechanics or hydrodynamics always do, which is the existence of some mesoscopic volume in your big system, where you have enough particles to assume that you have some local thermal equilibrium. But the system is small enough, so it's large to have some local equilibrium, but it's small so that you can assume that it's locally homogeneous. So it's mesoscopic. It has a size which is between the size of your whole system and the interparticle distance. And so locally you can define a temperature, a chemical potential, and a pressure. And so you have all these mesoscopic volumes which are in contact with each other, and so they are in thermodynamical contact. So it means that at equilibrium, all the intensive quantities like temperature or chemical potential, which are conserved, so you have transfer of energy between the systems, between the mesoscopic systems, so it means that the temperature must be homogeneous. You have an exchange of particles between the different mesoscopic systems, so it means that the chemical potential must be homogeneous. So T and mu must be uniform. So the temperature is uniform. It's very simple to imagine. So now, what does it mean that the chemical potential is uniform? So what is actually the chemical potential of the local chemical potential of your system? Well, if you go back to the definition of a chemical potential, it's the price it costs you to put or remove one particle from the system. So how much does it cost? So first you have a gas which has a density n of r and a temperature T. So it costs you the chemical potential of the homogeneous gas with that density and that temperature. But of course, you're also in a trap. So it also costs you the trapping potential V of R. So the local chemical potential is just the sum of the homogeneous potential at a density n and temperature T and the trapping potential. And so this quantity here must be homogeneous and must be equal to some value mu0 here. And so, for instance, if you know that this equation of states, it allows you to calculate the density profile of your system by inverting this equation. Okay, just a side note, this equation here is just equivalent with the usual hydrostatic equation, gradient of P plus potential plus external force is equal to 0 that you have in classical hydrostatics using the Gibbs-Duhem relation. Okay, so this is how you calculate the density profile of your system. But now I would like to show you that there is a way to invert this, this equation. That is to say, if you know the density profile, you can have access to the equation of state of your system, of the homogeneous system. So how do we measure, how do we probe atoms in an experiment? So we use usually absorption imaging. So it means that you have your cloud here, you shine some light, some resonant light along some direction, and you cast the shadow of the cloud on the CCD camera. So here I look at the direction Y. So what you measure in this case is the so-called integrated density profile, where you actually integrate the density along the line of sight, so along the Y direction. So this is the integrated, or the column density profile of your system in 2D. So now when you have this information on your CCD camera, it's very easy to integrate over a second direction. So let's say direction X. So I create this way the doubly integrated density profile, so n bar of z, so now it depends only on z, which is the integral over x and y of the density profile m of x, y, and z. And now if you assume that you are in a harmonic trap, Jason Ho and Quizu showed that you can actually directly relate n bar of z to the grand canonical equation of state of the system that relates the pressure to the chemical potential and the temperature. And so that's going to be my last calculation. So I assume that there is some trapping potential. So it will have some cylindrical symmetry around the z-axis, but it works also without that, just to simplify the calculation. So V of x, y, and z is equal to m omega perp square divided by 2 x square plus y square plus m omega z square divided by 2 times z square. So it's the trapping potential of my atoms. So, and this is what I call R square. So if I look at the doubly integrated density profile, so it's the integral over dx dy of n. Okay, so I know that dp is equal to n d mu minus s dt, where mu is the chemical potential, s the entropy, T the temperature, and P the pressure. So this is a Gibbs to M relation. A very overlooked relation, in my opinion. So we are dealing with a system where the temperature is homogeneous. So dt is equal to 0 in this system. And so you see that N density is equal to dP divided by d mu. It's just differential, the derivative of the pressure with respect to the chemical potential. So n bar of z is actually the integral over dx dy of the derivative of the pressure with respect to the chemical potential. And this chemical potential is just, so it's the homogeneous chemical potential. Here I'm writing the equation of state for the homogeneous chemical potential. So it's mu 0 minus V of R. And so here's the trick, is to know that, so it's, I have a cylindrically symmetric system, so I can integrate over the angle. And so this is actually 2 pi times RdR. And 2 pi times RdR is pi times dr square. And if you see here, the chemical potential actually depends on R, like R square. So it's actually minus pi. So there's a 2m omega perp square times d mu. This is mu here. So n bar of z is actually so minus 2 pi divided by m omega perp square d mu dp divided by d mu. So I integrate between r equal to 0 to r equal to infinity. So it means that the chemical potential will go from mu 0 minus m omega z squared divided by z squared to minus infinity. And so it's done because I have the integral of a derivative. So it just gives me the value of p between mu 0 minus m omega z squared divided by 2z squared and minus infinity. So a chemical potential which is equal to minus infinity corresponds to vacuum. So the pressure is equal to 0. And so I'm just left with 2 pi. So there is a 2 which is here, divided by m omega perp square times p in mu 0 minus m omega z squared divided by 2 and t. And so it tells you that just by taking a picture of a cloud like this, you have access to a patch of its equation of state. Because when you see n bar, you can see actually the pressure, and when you vary z, you actually vary the chemical potential here. So it's actually a representation of p as a function of mu. And when you know p as a function of mu and t, you know actually everything you need to know about the system to reconstruct all its thermodynamical properties using the Gibbs-Duhem relation, because by calculating dp divided by d mu you have n, and dp divided by dt you have s, and you can recalculate everything. So everything is hidden in this density profile. And so it's a very efficient way to work, because first you integrate your data, experimental data, twice, so it increases the signal-to-noise ratio. And usually when you make an experiment, you get 1 point on your graph. Here, when you make one shot, one picture, you get a whole patch, a whole piece of the whole equation of state. So you can use everything, all the density profile, to reconstruct the equation of state. So I guess I will go very fast through the next slide. So, for instance, you can probe this the equation of state of a gas of fermions at 0 temperature in the BEC to BCS crossover. So we write again using dimensionless analysis the energy of the system as the sum of the density, the energy of the molecules. So EB is density of the molecules when you have molecules, times n over 2. So you divide the number of molecules is the total number of fermions divided by 2, plus some function which is scaled like the energy of an ideal Fermi gas times some unknown function, dimensionless function of 1 over kFA. Just because you have only 2 length scale in that problem, just like Rudy described, you have 1 over kF and the scattering length because you are at 0 temperature. So there are 2 very simple asymptotic behaviors. So when 1 over kFA goes to 0 with negative values, you are in the BCS limit, so you don't have any bound states here, and you must recover the energy of the ideal Fermi gas, so 3/5 of NEF, so it means that psi must go to 1. And when you are in the opposite limit, so 1 over kFA goes to 0 by positive values, in this case you have a repulsive Bose-Einstein concept, and so you're dominated by the binding energy of the molecules, and so this dominates, so psi must go to 0. And so this is indeed what you obtain. So actually the experimental data correspond to the solid line here in black, and all the other points correspond to theory. So you can compare to analytical expansions. So for instance, here you have the Lee-Yang, so it's the dashed line here, Lee-Yang expansion. So it's the asymptotic expansion in the BCS limits. So the energy is equal to the energy of the ideal Fermi gas plus some infield correction plus some first order beyond infield correction. So they were predicted in 1957. and this was the first time they could be tested experimentally. You have the same kind of expansion on the BEC side with the Li-Wang expansion that was also discussed this morning, where you have the binding energy of the molecule, some mean field interaction, and some beyond mean field interaction. And so what is interesting here, again, in the spirit of this meeting, is that you see here that what enters the Li-Wang expression is not A, is not the scattering length, is what I call AMM, it's the scattering length between two molecules. So to know this, to calculate this equation of state, you need to be able to solve the four-body problem where you have two molecules that scatter. And so actually it has been calculated by Petrov for the first time, and this result was recovered using diagrammatic Monte Carlo by Brodsky and others. And the molecule-molecule scattering length is actually equal to 0.6 times the atom-atom scattering length. Actually, it might be surprising to get the Li-Wang corrections because that's obvious. We have a gas of molecules, and we know that at some point we must start to see that inside molecules we have atoms. So how far in the interaction strength can we just use the theory for point-like bosons to the case of composite bosons? Well, actually, the answer is known because if you push one step further the equation of state of the ground state of an ensemble of bosons, you get this term here with this log there, and which is not universal. So you see there is a number here, B, which depends on the details of your of the boson, of the potential. So the first two terms, so mean field and Li-Wang corrections are universal. They depend only on the scattering length between the bosons. So whether you have point-like bosons or you have composite bosons, they're the same. But then the next order term will depend on what's inside the bosons and will be sensitive to the internal structure of the bosons. So that's why the Li-Wang correction applies to our composite bosons. The inter-Fermi gas, so Rudy mentioned the Birch parameter. So this way you can measure the Birch parameter. So you already mentioned these numbers. I don't go into details. You can also measure the contact at unitarity, so dE divided by d1 over A. So here you have a dimensionless contact that can also be obtained experimentally and can be compared to fixed node Monte Carlo. You can also look at finite temperature equation of state. So in that case, you have another problem, which is that you need to know the temperature. So we are back to the issue of the thermometry of a strongly correlated systems. So two solutions were found. So at ENS, we've been using an auxiliary thermometer, which means that we work with a mixture of lithium-6 fermions and lithium-7 bosons. The bosons are weakly interacting, so we know how to measure their temperature. And if we assume that the two species are well thermalized, by measuring the temperature of the bosons, we have access to the temperature of the fermions. MIT uses a very smart methods where they actually don't need any kind of thermometer, but unfortunately I don't have time to detail it. But essentially what they do is that they measure both the pressure, I've shown you how to do that, and also the compressibility using a method which is called the Abel transform that allow them to measure directly N, not N bar. And using these two informations, they can reconstruct the temperature, recover the temperature of their system without any other information. And it's based only on thermodynamical identities, so there's no assumption except the usual assumptions of thermodynamics. And so you've seen already these plots where I show you the equation of state, so in terms of the pressure versus chemical potential for unitary Fermi gas. And so you have the red dot which corresponds to MIT. Our data are in this one, the diamonds. There's Tokyo here, and you have all kinds of theory. But again, what is nice is that we can compare directly, independently, the theory and the experiment. And so I've reached the end of my talk. So I hope I've convinced you that we can use model-free schemes that rely on very little assumptions, so very general assumptions, basic thermodynamics, some some very simple scaling identities. And this way, they provide some solid foundations for the quantum simulation program, because when you're in a situation where theory is no longer reliable, you don't have any help from the theory to get some quantitative results to your experiments. And so it can be extended to other systems. So I told you in certain limits, you can extend that to strongly correlated boson. You can also introduce new parameters like three-body contact parameters for the bosons. You can also look at these aspects for low-dimensional systems. And I thank you for your attention.